What? Did I not have it set up? Okay. Cool. So getting started with this, this is an introduction to parallel processing, what that is, and then how to use some of those applications on HPC, and also how Hadoop, Apache Hadoop, can be incorporated with that. So there's a lot of jumping around a bit, but we'll start off with just the general idea of what parallel processing is, with a focus on how to do it in R. So with standard computing, you might think if you have a script or something you're trying to run, it's basically a list of instructions, and those get fed in one at a time through a computer or processor in this case. So in the diagram down below, we have some problem that we want to solve, and so we break it up into individual instructions, and they go in sequentially through this computer, and then the computer analyzes those and spits out the results at the end. If with a setup like this, the bottleneck here is the processor itself in this case. So a setup like this would require a fast computer if you wanted to run things faster. And here the only way to actually get answers out more quickly is to have the computer run through them faster. But there's another way to do that. If we look at parallel processing, which is where we can actually split the problem up into different chunks, and then we can assign those chunks out to multiple computers. And so what this does is it adds an extra dimension where instead of making our computers faster, we can also increase our computation time by spreading out the job to multiple computers, reducing the load on each one. So if you're, for an example, if you have to make 100 sandwiches or something, you can either have one person who can make sandwiches really, really fast, or get 10 people to each make 10, and you end up with your answer the same way. So problems like this show up a lot with what we do with data science, because we usually have a method that works, and then we just need to apply it to a bunch of different data sets. And so we can just take the one method, split up the data sets, and run it over a large number of processors. One of the basic examples is it's numbers of computers versus speed of computers going forward. There are still some problems that have to be run in serial, especially ones that involve a changing state and calculations that depend on that current state. So you actually have to calculate what the state will be before you can keep moving forward. And for cases like that, you still need to do it sequentially. But for most cases, and especially with data science cases, popular things like resampling multiple data sets or things like that can be done very well in parallel. Also, there's a very important scalability factor with parallel processing, in that if we need more computation speed, we can add more computers to our framework. Whereas if we have a standalone computer, it's difficult to make one computer just move faster, because that's quite often a hardware limitation. But you can see here, if we have one master and 3 workers in this case, if we add 2 more workers to this, then we have increased the scaling capability of this. And this also works with storage in parallel as well, distributed storage, which we'll talk about in a little bit. If we need more space to store things, we can just add more hard drives and get more room to work on stuff. So now we're going to do a quick look at some parallel processing in R. And this is pretty nice because we can do it in a cluster, which is what HPC is. It's a large number of group machines, or we can even do it on a local machine. So if we jump over to RStudio for a sec, can everyone read that? What's this? Hide, go away. Okay, so this is just a quick RMD. And so there's some documentation on here about the do parallel package that we're going to use. So you can start digging into that more if you want a bit more functionality from this. But there's a couple different ones to use, but do parallel is the main one we're going to be using right here. And so we have this, we've loaded this in, and we can use this function to detect cores to see how many cores I have available on the computer. It pops on here. I have 4 cores. This is a quad-core processor on this computer. So this is one processing unit with 4 cores in it. So theoretically, I can split any problem up into 4 chunks and run those individually going forward. So if we move down, if I'm running this with do parallel locally, I have to manually set up a cluster for this. So I can start up by just assigning some number of cores I want to use, and I can either use the maximum number, or I can reduce it a little bit depending on what I might want to do here. And then I can use the make cluster function to assign this as a cluster. And then I can do register do parallel C1. And now I've built my cluster instance here. So from here on, I can submit work and have it run in parallel just on my local machine right here. And I only have 6 gigs of RAM on here, so I'm not going to see huge improvements with this, but it's a pretty good idea to sort of wrap your head around how some of this stuff works. So then once you have your cluster set up, this for each function right here is used in the package to help define what you're iterating over. And then you have this do par instance right here that can set this up. So this is a very simple example. And I assign for each as 1 to 10,000 and then do in parallel square root. So what this does is I've given it a list from 1 to 10,000 to run in parallel. So it knows that this list from 1 to 10,000 is what it can split up and spread between the processors. And then within each processor, do the square root of whatever it gets. So if I run this, and it shouldn't take too long, and then I get roots, which will be a large list of square roots. So not that impressive. But this is sort of the basic setup for all this other stuff you're going to do. And then I also need to stop the cluster to free up the resources after it. So the next thing we can do is we can do a time test to see about what we're getting out of this. So there's another function here, register do sequentially. And what this will do is it will allow us to run things serially, but we can still use the same notation as if we were doing in parallel, which is pretty nice. So this is pretty straightforward. I don't have to assign any cluster to get this going. I can just start it. And if I do get do sequential workers, I get 1. So it's just running sequentially. So I only have 1 processor available to do this right now. So in here, this is a bit of code. The code itself isn't really important. It's just calculating and resampling a large number of models. But what we're doing is over the entire time, we're tracking how long this takes to do 10,000 iterations of this. So I'm already in my serial instance, so I can run through and set this up. And that error pops up sometimes. It's usually not an issue. It just had one of the pathways was still open before. So this will run for a little bit, and it usually takes about 20 seconds. We'll see how long it runs out. If anyone has any questions along the way, just feel free to ask. A little bit of waiting. The fan on my computer starts up. There we go. So if we look at what we get out of that, 24 seconds. So a little bit slower than before. Now if we run the same code in parallel, so we're going to do what we did before, make our cluster as parallel. And now we have 4 workers instead of just 1 if we run the exact same code. So if we look at the setup before, we define our iterations, and then we say for each in the iterations. So we know that the number of iterations, it's what it's splitting up. And then within this do parallel instance is these lines right here, and that's what's being assigned to each of these separate cores as it runs. So what did I last run? I ran the parallel time. So that will go through. And this will take less time, hopefully. It usually does. Here we go. So close the cluster, and we check the time again. So it's gone down to 12 seconds. We basically cut the computing time in half between these. And you might think that it's a bit weird that we have 4 times as many cores, but we only have half the time. But there is a little bit of overhead as far as assigning the cores go. So it might not always be beneficial to get as many cores as you possibly can for everything. If you have 10,000 data frames, you might not want 10,000 cores to run them, especially if the computation is pretty small, because there's time it takes time to partition this out between all these cores and get these running. So we didn't get quite as much as we might have thought we would, but we still have cut the time in half on this. So it's pretty useful here. And there's some other things you can do within the for each as far as organizing your results. It's very useful. So I have some setups here, and we have 2 extra calls in the function. We have the .combine and the .packages calls. And what each of these does is it organizes how it structures the results. So when you run these, it takes whatever iterator you give it and runs it for every single one of those. But then when it recombines them, you can tell it how to do that. So in this case, it will row bind the results together. So it'll stack rows of each iteration on top of each other, we can do this with cbind as well and have each one be its own column at the end. And if we want to use packages within the script, then we can also do this .packages and load whatever packages we want at the beginning to save us some time going through so we don't have to load it every single time we run through. In this case, I've loaded dplyr and ggplot2. I use the mutate function in dplyr. I didn't use anything in ggplot2. That's not really a problem. So if I run through this, register again, run through those, and I've dropped the iterator by an order of magnitude, so it should go a bit faster. Go ahead and stop the cluster. And if we look up here, let's make this a little bit bigger. So we have roots as rows, and so this is what we get if we row bind them. So I just have the square root, and then I mutate the square root as a new column dividing by 2, just to show off the dplyr a bit. So these, now we have 2 columns, and then we'll have 1,000 rows because we have 1,000 iterations to run through. If I look at the column binding, this one is a bit more ridiculous, but there are definitely ways in which this would be useful. So now for every iteration, and then for the mutate, it creates a unique column for each. So I have 2,000 columns and only 1 row for this. So a lot of times in data science, the row bind is what you might want to use. But if you're doing, say, model building, then the column binding might be useful. It really depends on what you want to get out of this as you're going forward. Okay, so that's a little bit of a demo on a local machine about how some of the clustering can work. So if we keep moving forward, then we can start moving on to high performance computing. And the first thing to do is always go to Wikipedia. But if you go to Wikipedia for high performance computer or high performance computing, you get redirected to supercomputer. So it's not a very well-defined term generally, but how we use high performance computing is that, back up there. So there was talk earlier about number of cores versus speed of computers, but you can very easily just take really good computers and have them running in parallel with each other. So a combination of both, and you get the best of both worlds. You get fast processing over a very large distribution, and that's what we consider to be high performance computing. And this is definitely where the high-speed computing is going in the future. It's getting really good computers to work very well with each other. And we can also integrate data storage with that, as we'll go over in a little bit. So we use the, this is the Case Western High Performance Computing Cluster up here. So shout out to these guys, because we could not do the work we do without this cluster. And they have very good, they've been very helpful in the future. So if you're using the one on Case, you ever have any questions, you can jump over to their website, and they have this Google Sites page that has pretty much all the information you could need about getting started and running some of this stuff. So there's a lot of different aspects about the high performance computing cluster we can talk about. But if we're just sticking with parallelization right now, then we use Slurm jobs for this, which stands for Simple Linux Utility for Resource Management. Is not the soda from Futurama, unfortunately, but this is just it's another open source tool. We like not paying for things; it's always useful. But basically, this is a manager that helps us organize how we spread out and partition these parallel jobs that we give it. And this comes with a couple built-in functions that we can use. And there's also examples in HPC on how some of this works in a couple different cases. So if you want to load those onto your local instance, you can use this command here. Just copy the file of the examples into wherever you are, and you can run out from there. So if we go, we can jump over and take a look there really quick. So we use the X2Go client to connect to HPC here. Start my session. Let's just do that. So we could connect to this, we could just SSH through a terminal to connect, but then we can't run any sort of graphical software from that. By using X2Go, this gives us options of running things like RStudio or opening PDFs or things like that in HPC land. So it's very useful as far as doing more dedicated work up there. And screensaver takes a while to show up. There we go. That's new. Didn't know it made a noise. So if I open up a console here, oh, come on. There it goes. Let's see. Let's zoom in a little bit. Was that Control Shift? There we go. All right, how's that? So when you first log in, you'll be on one of the login nodes, HPC1 or HPC2. However, you don't want to do computations on the login nodes because they'll send an email to you and kick you out of the session, which has happened to me before. So what you need to do for this is actually request a compute node if you want to run some computations on. So this is srun -x11 -ty there we go. And the srun is a Slurm function. And I'm basically just submitting a job to request access to a compute node to work out of. The x11 is the resources of the compute node I request. I could also request specifically a number of compute nodes or a number of CPUs on a compute node, something like that. So whenever you run a job up on HPC, you get a job ID here. There we go. And so when you first run it, it queues up. And then here it's been allocated resources. So now my terminal should pop up and it should be different as soon as this goes through. There we go. And so I've moved from the login node HPC1 to the compute node 168T. And we can do, if we do a little bit of a comparison between this compute node and my laptop, we can do ls CPU. And we're a bit zoomed out here, but we can see here I have access to 16 cores on my laptop, or on this compute node versus 4 on my laptop. This has 2 processors on it with 8 cores in each one. Just a bit more about that. And if we do free, we can look at the RAM. Do free-h, we can look at the RAM better. So this one has 62 gigabytes of RAM. So this is the idea that we have a lot of really good computers. This is far more than you would ever see on any conventional computer, any desktop you would own. Usually they're about 8 gigs of RAM, I think is pretty standard. But we have about 4 times as many cores and 10 times the RAM just on one of these compute nodes. And we have about 200 of these nodes we can get access to. So this sort of gives you an idea of how much this can expand outward and be applicable to very large data sets as we move forward. So let's move over to where I have some of these examples saved. There we go. So these are a couple scripts that they have set up for this. And if we look at the multi-core one, just pull that out. So this is the R code for this one here. And this is the same code that we were running in the example we did locally. So you can see here this script basically reads and do parallel and does essentially the same thing we did before. And it outputs the time it takes to run that. And then if we're trying to submit this on HPC, we have our script, and then we need to submit the script in a batch job. And so here we have multicore test.r, and there's this multicore.job right here. This is the bash script that will submit this job to run. So if we take a look at this, and this can also be .slurm as well, it doesn't have to be .job. Multicore.job. So it's the bash script that starts out with the standard notation. I think that's called a shebang or something like that, the # exclamation point. And then we define the parameters for the job we want to run. So in this case, we have requested 1 node and 2 cores on that node. And then the rest of this down here is just the basic stuff for running the job. So we have to do a module load to get our working in the environment. And then these two lines right here are important. So this builds what's called a scratch directory. And if we're loading data, we don't want to load it on wherever node we happen to be in. We want to build a special place to pull up all the data in, run the analytics, and then we can just delete the scratch directory so we don't get a bunch of extra memory leak running around the place. So you'll want to use this. But the good thing is this variable is an assigned scratch directory, so you can use this anytime. This really doesn't change between them. And then this is an extra line they added just to show us the number of processors we get. And here is where we run our script. So this should be very straightforward. And if you have your code organized well in a proper pipeline, you can pretty much use this thing as a template and just move in different scripts you want to run here. So right here we have 2 cores for this. So if we want to run this, we just do sbatch and then multicore.job. And we have submitted the batch job, and we have this. So if we want to see what jobs are running, we can do sq. This is another Slurm one. But if we run this, we're going to get every job that's running. So this doesn't help us very much. If I do sq, this word, I can't spell it, 269. So I only want the job submitted from my username on here, and we have 2 running now. We have the multicore one that we just submitted, and we also have the bash script that I'm using to be in this compute node currently. So if you're in a compute node, I have a running job that's connecting me with that compute node. So if we take another look, if we kept staring at this, we'd see eventually this one would disappear when the job is finished. We can see right here in status, it's running. And something else important to note, the compute node it's been assigned to is not the one we're currently on. And that's part of the resource allocation. It figured out which node would work best for this job, which is the earliest available, and it assigns it to that. So while we're, yep.
Dash U, flag G work for group?
I don't know. So
I'll check it out later.
yeah, I'm not sure, but you can check out for that.
That would be very useful.
Mm-hmm. Oh, to keep an eye on what your group is doing? Yeah.
What my group is doing.
Okay. You can use grep works with this really too. So I could also do sq and then type that into grep AJC 269, and oh, my job finished. Look at that. And I can also do, if I do the same thing, but I can look at a specific node. So we're on comp 168T. So, and also I don't get, if you don't get your own node to run stuff on, there's always other jobs running on nodes, but it's all partitioned and organized based on Slurm. So I can see on the node that I was just using, this is the one I'm currently on, 168T. There's other jobs running on here too. I'm just here as a part of it. So I don't get my own special little node, which would be nice. So if we look at our directory, if you all remembered what was there before, then what was not there was this file right here, the output. So we get an output based on the job that was given to us. So if we take a look at that, that's one here. So we assigned 2 processors for this, and then it just basically spits out what was printed to the console. So right here, we printed out a 2 to the console, and we printed out the elapsed time, which was 23 seconds for this. So this is this took more time than locally, but that's because it's a very short script, and there's a lot of overhead to getting this set up. But if you have a large, so if your script takes 20 seconds to run, you probably don't want to submit a batch job. If it takes 300 hours to run, then a batch job is a bit more like what you'd want to see. So if I want to speed that up a little bit, for example, I can just go to my file again. And if I go over here and change this to 12, then sbatch again, core.job, sq -. So now I have this job submitted again, and it's already running, which is nice. It's been given a separate compute node now, compute 069T. I think that one has 12 cores on it. So we've got a little bit of everything in there. This one should be a bit quicker to run. Yeah, see, it's already done. So if we look here, now I have another out based on the job I submitted there. So if we take a look at that, 5.1, there we go. So now it pulled the 12 processors as expected, and we went down to 5 seconds instead of over 20 seconds for this one. So that seems to have worked pretty well. So an example of a real pipeline that we've used with this, if we look here. So if we template. So this is a setup that a previous grad student and I have used before of running a pipeline here. So this is what a standard one would look like. And as a pipeline setup, what you want to do is write everything as functions. And then your pipeline is a script that incorporates all your functions and takes an input of a file or the name of a file, reads it, and just runs it through all these functions and spits out your answer at the end. So you don't want to run one function and take that, run in a different function. This works best if you have one script that runs your entire computation process going through. And we've split that script up into separate functions through here. So we have reassemble, rename, data cleaning, a saturation test, resample for some statistics, our predictive model, things like that. But it's all located in this main script function here. So right here, you can set a working directory if you want to. My advice would be don't ever use relative pathing like this, because when he set this up and then I tried to run it, the tilde means your home directory, if you don't know that, but it's dependent on who's actually logged in. So when Yang wrote this out with tildes everywhere, that was from his home directory. When I tried to run it on mine, it was different. So none of the files could be found anywhere. I had to go through and redo every single directory through here and dig through all the functions. It wasn't fun. But if you replace the tilde with /home/ your username, that's your home directory on HPC if you're assigned one. So anyone else will be able to run your code at that point if you want them to. So here what we have is we read our stuff in with, we have a CSV of names of files to read in. So all you have to do is load that in. And then here's our familiar for each do parallel session. And so what we do is we have this list of files we want to read, and we just feed that straight in. This is the only function we have in our parallel instance. We just have this list of files, and we feed them in parallel into this tf main function. So this makes the parallel script very easy to write and set up. It makes it a lot easier going down the road. There's a try catch around this. This is really nice in case one file goes south, it won't crash the whole thing. So you can throw that up around there. And then all of this is assigned to this sum.table, and then we just write sum.table out. And this is also, this is row bound, right? So we get a bunch of answers, some statistics about it, we just row bind them together, and at the end, we get a table that's the result of the analysis we ran on all these plants. So it's a very nice, concise way of running this analysis. And if you set up your pipeline properly, it's very easy to edit. So a bit of an idea of how much time this actually saved us. Running one of these sites on a local machine took about over 30 minutes because there was a large resampling done with this. And I think we also made a pairs plot, which takes a long time if you have a large amount of data. And so we had about 1,100 systems we wanted to go through with this. So that's pushing 500 hours to run this if we were going to do it on local, which really wasn't going to work because Yang had to graduate. As we set this script up, this took about 4 hours to run the entire thing, and we weren't even that good about partitioning the resources. So this was just one node running a high number of cores with a higher memory allocation to get this running through. We could actually spread this out between more nodes, get it allocated a little bit better. It could take minutes to run something like this. So the kinds of analysis we want to do with our work in data science would not be possible without the setup from HPC and this parallelization we can run with this. So we're very grateful that all of this is around and works pretty well. So always be sure and leave your compute node before you go there. So we'll jump out of that. It's a little bit of a demo. Close out of X to go. And if we jump back over to the slides here, so the last subject here is Apache Hadoop. The cute little logo down there. I'm not sure where Apache comes from, but Hadoop is the name of one of the engineers who built this. His child had a toy elephant named Hadoop, so that's where the name and logo comes from, I guess. So pretty nice. What I've been talking about so far is parallel or distributed computing, but we can also do storage in a distribution as well, which is really nice because, again, the biggest problem with storage is you're going to run out of space. Or if you have a very large amount of data, then you can have a lot of trouble reading through that. If you've ever opened a large CSV in Excel, then you'll kind of get the idea of that. I've had some pretty bad experiences trying to do lab reports out of Excel with large data files. But the idea of Hadoop is that we can take these data files, split them up, and organize them over a large number of hard drives, and that will give us a lot of power over how much we can store and how quickly we can pull answers out of it. So what Hadoop does is it's an organizer for this distribution. It keeps track of what's going where, and if you need information out, it can organize that for you and help you get that set up. You can check out their pages. So again, Hadoop is open source, the running theme. And all of this was started from a paper Google put out about MapReduce. And if you've ever actually thought about how much computation an average Google search has to do, the amount of web pages that get filtered through when you're just searching for a picture of a cat or something like that, it's pretty amazing. So Google's definitely been on the forefront of this, and they pioneered this MapReduce model that they have set up. They've since moved on from that. They have bigger and better things, but MapReduce is still a very useful tool in most cases. I'm not really sure what they have now. I'm sure it's very proprietary and way over my head. But this paper here was sort of the start of the fire of all this distributed storage. So if you're interested in looking at some of this, this is probably the best way to start because this is the one that started it all. I believe this paper has about 20,000 citations, so it's definitely gotten around. So the structure of Hadoop, there's three main components to Hadoop. You have HDFS, your Hadoop distributed file system, the area where all this is stored. You have MapReduce, which is your model for assigning programming to all of these. And then you have YARN, which stands for Yet Another Resource Negotiator, which is a resource negotiator. It helps monitor the resources across this distribution. There are a lot of other utilities available in this. There's Pig, for example, is a language for ingestion and querying and things like that. Spark, HBase, Hive, all that are utilities that are also available in this structure. Pay close attention to HBase and Spark because we're going to be getting into those a lot more. Those are the ones we're using in our group. We've used Pig before too, but Pig is for a bit larger data scale than what we use. However, it is very straightforward. So Pig makes things nice and easy, but it is a bit slow for what we'd like. So the storage structure for this all works around the idea of that if you're running a computation, normally you would think you have code somewhere, you load in your data, you run it, and then you can just ignore the data and keep your results. But the idea of the Hadoop setup is that if everything is distributed across the system, you can actually take the code to where the data is, run it on there, and then organize your results after here. So the hello world of Hadoop is the name count function here. So if we have an input of random words, deer, bear, river, car, river, deer, car, bear, when we store this in, it gets split up and distributed across, in this case, we have 3 drives where this data is stored. And then if we want to figure out how many words of each are across our entire cluster, then we have to go into this mapping phase where we take our function of word count and we spread it out to all the data. And so on each one of these nodes, it's going to run this function on the data it has available there. So it's taken what could be a very large data set and split up the computation into what data is on a single node. So each node will run the calculation on its data, and give the results. And then we have the shuffling and reducing phases, which are often thought of just one phase at the end. And what that does is it takes the results it gets from all of these, organizes them, and reduces them down to a simpler output. So in this case here, we have a read from each one of our nodes. So we organize them, however many we have, and then we combine the results from all the separate nodes into one list to get our answer. And so this is how the MapReduce runs through large series of data to quickly pull out answers that it might want to do. And this can be done with a lot of other stuff. You could do mean distributions, things like that. But generally speaking, you don't want to have huge analytics in a case like this. But for very simple queries or things like that, it works very well. Something else about HDFS is that it stores data in triplicates. So if anyone's ever had a hard drive or flash drive fail on you, it can be pretty annoying. And since Hadoop is made up and runs over a very large number of hard drives, it has to account for system failures as being something that has to be accounted for. So it takes care of this by replicating the data 3 times across different hard drives. And that way, if one hard drive blows up or fails or something like that, you won't have a massive loss of data as a result of that. You'll just lose one part of it, but it exists in 2 other places. So that's one of the things about Hadoop is you need a lot of storage because any data you put in gets replicated to be 3 times as large as it is, which in recent updates, they've reduced that down and made it a bit more efficient. I think it's now it's closer to 2 times as large, even though they have it spread out a bit more. But that's more on the cutting edge of what's Hadoop is working on now. But this way, you won't have, it's almost impossible to lose data in a Hadoop system because it's got 3 different locations where you could potentially pull it from. And this is also accounted for when you do a MapReduce. It also knows what data is duplicated because it has all that flag. So that's part of the reduce, is to kick out redundant results as it's going forward. So how we, just to kind of wrap this up, is how we use all of this. This is all based around what we call Energy Cradle. And it's, so we do degradation analysis of photovoltaics on the large scale. There's other subgroups that we work on, but we have a lot of different data from a lot of different sources. So we have power time series, we have material data, we have IV curves, things like that. And the idea is that by using this distributed storage and computing structure, we can bring in a large amount of data from many different sources and then run large-scale computations on them, but keep everything organized and running smoothly within this setup. So you can see here we have a lot of different types of modeling that we use and a lot of different data sources. But given the nature of this database that we have set up, we can actually store anything we need to. And this is sort of leading into next week, or tomorrow, I think, is when we start talking about HBase, is the storage for this. We can store pretty much anything in one place with each other. So we can store image data and CSV files in one table if we have it set up right. So we can organize these vastly different data sources, but still run consistent computations on all of these. And because of the scale of all this, we can basically take as many data as we can possibly get, as we can be given by anyone, which is always good as far as broadening out the statistics and looking at some of the answers we're going to get. So I think that's about all I have for today. If anyone has any questions before we close up, I can try to help you out. All right, thank you very much then. And let's see, where's the YouTube one? Is this it?